Hi guys, this is lesson number 2 out of Proton NMR Spectroscopy. The first lesson I went through some of the basic principles, well, sort of how to look at chemical shift values. It wouldn't have made any sense to you whatsoever, but it should do start to come together a little bit. Now this second lesson, again, I'm still sticking with low resolution proton NMR. High resolution will be in the third video. High resolution will incorporate the splitting, that sort of stuff, okay? So we're sticking with low res in this video just to give you some idea again of the basic principles before I introduce splitting patterns into the equation. That's the plan. So this is your second lesson, guys, on this. Right, let's have a look. So let's take, for example, first example, right, of a low resolution spectrum. Let's take this. CH3, C, double bond O, H. Right, first thing to think of is what environments are there in that molecule. Now I urge you to do this, okay? So what environments are there? You've got one proton in that environment and you've got 3 protons in that environment. Simple as that, all agreed on that. Now I'd like you to be able to do a little bit of a table when you do this. So these tables will develop and get more useful shortly. But let's have a look. The table looks like this. Tiny little table. This is something, because you get marks for this in the exam, even if you can't interpret what the actual molecule is, to show that you've interpreted the spectrum and written them in a table means you're going to get lots of subsequent marks. So you're going to get a fair few marks even if you can't get the actual structure of the compound right. So this table I need to concentrate on here. Chemical, so, no, what will we have? What we have? Hang on. ENV, that's right, it's all coming back. Chemical shift, int. That'll do for our very first little table, but force yourself to do this every time you do one of these, okay? Environment, right. Look on your data sheet, okay, and see what we've got. 3 attached to that. Is there anyone on that data sheet? Yes, there is. Environment, H, C, H, C, double bond O on there. Those are smack on those. If you look, 2 to 3, 2.0 to 3.0. Integration, I'd expect that peak when, in terms of its overall relative peak area, there are 3 in that environment. I'd expect that peak essentially to be 3 times bigger than that peak. Okay, well, don't worry about that. 3 integrated to 3. The area under a peak, 3 protons in that environment. This one, by contrast, bear with me, is this. C, double bond O, H joined directly to the carbon of the double bond O. H joined directly to the carbon of the double bond O. These H's are joined not direct to the carbon of that, they're joined to a carbon which is then joined to a carbon of that. They ain't the same. So if you look at that, this is a classic aldehyde chemical shift proton, basically. So if you look at your thing, you don't get these very much, but between 9 and 10 is a giveaway. 10.0. We'll look at these numbers in a minute. So that's telling the examiner that you've identified exactly what the different groups are, what the different environments of each proton are, what the subsequent chemical shift is, and what their integration peak is going to be. Normally you go backwards, you take the spectrum, and then you deduce this from the spectrum. You'd obviously, so we're sort of going around in reverse order, but that's absolutely fine at this stage. So, time for me to draw a spectrum. Right, and I won't be doing necessarily, so we'll take this one nice and steady. So up the side, what is it? I don't know, you'll have to say, I can't remember what, the absorbance or something, I have no idea, I'm not interested. Chemical shift, ppm, okay, 12, 0. Normally, well, we'll 6, 3, 9, 7, 8, 9, 10, 11, 3, 4, 5, 1, 2. Alright, there you go. Right, what we're going to get. So low res, sticking me low res. Oh, found another pen there. That's nice. There's a flipping lid. Sorry. Where's my lid? Where's me? Oh, I put the wrong lid on. I'm a bloody idiot. Bear with me, bear with me. I'm just faffing about as per usual. Right. So what's this spectrum going to look like of this? Of what is this? Whatever it is. What is it again? Ethanol. Ethanol. An aldehyde. Okay. So dead easy. You're going to get this. Do it in 0 is your tetramethylsilane peak there. Okay, a peak there. Why is it there? Between 2 to 3. 2 to 3. 2 to 3. Crap on the end. Between 2 and 3. Right. Between 9 and 10. Peak. Again, right. No splitting patterns at all. Nothing at all. We'll discuss that later. We're going to come back to this and discuss the splitting pattern later. Now these peaks, there is I suppose, without getting too mathsy about it, when you integrate something, you find the area basically underneath the peak, the total, the relative peak area. You can't tell by looking at them, but I've tried to make that one 3 times bigger than that, but in a real NMR you won't be able to do that. But you'll have this, and for mathematicians this should help. You sort of have a thing, a sort of a trace overlaid, right, and it normally tells you. And this is an integration of the peak area. Those of you who do maths and differentiation and integration will have a vague idea. Either way, we don't care. That will tell you there's 1 proton in that environment. This is called an integration trace, that there's 3 protons in that environment. That is the NMR spectrum for that baby there, for ethanol. Okay, cool. All right with that? Cool. Right, gone. Now, let's do another one. So I'm trying to rub out certain bits here and keep certain bits. Save me a bit of faffing about. Alright. Keep that there. Keep that. Keep me table. Must draw a table when you answer these questions in the exam. Okay. Number 2. Sound. Here we go. Number 2. Right, what's on my list for number 2? Propanol. Very simple. CH3, CH2, C, double bond O, H. Right. Okay. First of all, how many different environments are there and what is their chemical shift? Right. Let's go. Let's go from the right hand side. Okay. Same as the last one. Right. Again, I have my thing in front of me. I look and I'm looking H joined to a C, directly joined to a double bond O. So where is it between that? So H joined to a C. Stand like this way round on the sheet. There. Chemical shift 9 to 10. Notice I put 9.0 to 10.0. We've got to be a bit accurate with these. You've got to watch out. Integration, pound to a penny, 1. Because there's 1 proton in that environment, that one there. Okay? Number 2. There's 2 protons there in this environment. Right there. Okay? So what's all that about? Right. Okay. 2 protons there. Look at your chemical shift. Those protons are joined to a carbon, which is then joined to a carbon. Never mind these. Then joined to a carbon, joined to a double bond O. That is the key driver of where they're at. So you look on here, and I see this. C, double bond O. C, H's on it. Those 2 there, exactly what we want. Okay, and those are between, I told you this was a popular area, 2.0 to 3.0, and I'm expecting that peak to integrate to 2 because there's 2 protons in that environment. Finally, this one you've never met before, and this one is very much prone to splitting because you've got adjacent protons here. On the adjacent carbons have protons on them, should I say. Again, they will interfere with each other in high res. They will split, and you'll be able to tell things from that. But we'll deal with that, like I say, later. So we've got 3 on there now. Well, what function? What environment are these? Well, this environment is this right at the end. That R isn't necessarily, to me, an alkyl group, right? Because you could think that those 2 are joined to a C, which is joined to an R, right? Well, it's not. These, it's H's. It's what this chemical shift is: protons joined to a carbon that are then joined to a carbon with in a chain with protons on it. Okay. So, I haven't explained that very well, but take my word for it. When you get a hydrocarbon chain here, those 2 are sort of dictated their chemical shift by this C double bond O, but these 3 here are straight away in the 0.5 to 2.0 region. When we do loads of these, you will see, and and they are H, C, R. Those there. You might say, oh, well, they don't look the same because isn't that an R group there? Isn't that those? No, it ain't. H is joined to a carbon, and I suppose that R is CH2. That's the way they say it. I don't know. Okay, but that's the way it is. Okay, now how many have you got in that place? 3. So, if I draw my spec, I'm going to end up with something like this. TMS. Right. Then 0.5 to 2. 0.5 to 2. A peak for these there. Not the best peak in the world, but it'll do. Okay. Then 2 to 3. Then 9 to 10. Integrate now. I haven't drawn those peaks to scale. You will be told that's your TMS. That's your standard. That's where you calibrate from. That gives you your starting point for the rest of the scale. So ignore that. Right. So take that out of the way. Let's be clear. That is that. Those 2 there. Is that. Those 3 there are right on the left hand side, on the right hand side there. Okay, now integration would look like this. Overlaid with some mathematical stuff. Oh dear. Right, and you are going to get on there. They are supposed to be relative heights. Don't worry, it's a mathematical process. All it's telling me is this relative peak height. 1, 2. There's 3 in that environment, 3 in that environment, 3 in that environment, 3. Okay? there you go. That is your second low resolution NMR of Proton. Okay, guys. Cool. Right, one more, because these are going to take quite a long time. It's not something you can rush. Okay, so that's the way it is. You go through these very carefully, very slowly. You follow the stuff and you learn it, and that's the way it is. Okay, so I'm going to do one more and then that's it for this video, otherwise it'll be too long. Right, I'm speeding up onto a classic here. Now, let's do an ester, okay, because they're classics at low res and they're classics at high res too. So, right, now, I'm going to do my next video. I'm going to do lots of these, so I'll just finish off with one. Okay, so I'm going to draw an axis there. Okay, and the molecule I'm going to consider is an ester, really classic, CH3, C. Bondo, Ingobondo, CH2, CH3, and over here I need this environment, chemical shift, integration. Right. Let's have a look. Start on the right hand side. Now I'm going to, I know for a fact that all these, I'm only going to go up to 4 in my scale, not 12. I don't need to go that high, so I'm going to just stick to 4. And the ones I'm going to do when I do esters, different configurations of esters, they're very useful for showing splitting. I'm going to go chemical shift wise just up to 4. I think that's absorbance. Not up to 12. It's a waste of time. 0, 1, 2, 3, 4. Right, let's bang onto this environment going over here. H, C, R. Right, I'm telling you. Right, HCR, chemical shift 0.5 to 2.0. I'll put the labels on in a minute. This here, HC single bondo, HC single bondo. Over here, HC C double bond. Oh, that's it. All right, now let me explain what's going on here. So, 3 to 4. I could just keep it 3 to 4. Those chemical shift. Lost my flipping danger sheet here. 3 to 4. These are going to be 2 to 3. Let me just check. 0.5 to 2, a lump of hydrocarbons, well away, hydrocarbon sort of thing going on here, about those there, those 2 there joined to a carbon, joined to a single bond oxygen, these 3 here joined to a carbon which is joined to a carbon double bond O, which is between 2 to 3, joined to a carbon, joined to 2 to 3, right? Integration. I've got 3 in that environment. I've got 2 in that environment. There. And I've got 3 in that environment. Those. Okay, so what's it going to look like? Move to red. shall see. Okay, so here we go. Between 0.5 to 2, little TMS. Okay, again, low res, 0.5 to 2, so I'm going to stick it at 1. Peak. Okay, 2 to 3. Peak. Put them all the same size, it doesn't matter. Peaks proper. 3 to 4. There's the peaks. Integration trace. Again, this shouldn't necessarily be, so don't look for scale here, because it shouldn't necessarily be to scale. There. Right. There. Right. Let's break this down exactly what I've got here. Let's make sure that it's absolutely spot on. And it is. So I've got 3 protons joined to a carbon, which is joined to a carbon with protons on it. Those 3 there, take my word for it, those 3 there are those responsible for that peak there. So the integration on that peak is 3, because there's 3 in that environment. Okay, moving along, protons joined to a carbon, joined to an oxygen, protons joined to a carbon, joined to an oxygen. 3 to 4. Okay, so, and there's 2 of them. Okay, so 2 up here. So those 2 there. There. Finally, 2 to 3 protons joined to a carbon, which is joined to a carbon with a double bond O on it. Those there. 2 to 3, popular area. Those 3 there are responsible for that peak there, integration value of 3. So that is the low resolution NMR spectrum. These are going to split each other. I can tell you that for nothing, because there's protons and adjacent carbons. They're going, the signal is going to interfere. So the signal actually, and don't worry about this, between that one, it's not how close the peaks are, but that one, those protons there, and these protons here, which these are going to be split. They're going to interfere with each other, and the peaks are going to be split. Okay, that will come later. So in the next video, I'm going to do some more examples of low-res NMR, and I want you to do them with me and think about them. You will get worksheets sent through with these examples on. You need to be able to do them as a first step. Okay, it's going to take me a few to do this, okay, because it's not something you can just teach straight away like that. Okay guys, I'll see you later.